this episode of Woodlands on the Web, we'll be looking at an example problem from the equilibrium problem set to see how calculating the reaction quotient and comparing that to our equilibrium constant allows us to decide about the equilibrium shifts. By this point in the problem set, you should be fairly comfortable with writing a equilibrium constant expression. So I've already done that step here for you. So you have the equation for the formation of ammonia. And again, we're putting the products over the reactants and raising those individual species to the power that matches their coefficient. Okay, so in the next step, we're going to calculate Kp, and then we'll move on to doing some newer things with these numbers. So part B provides us with partial pressures, and that's going to be how we do the calculation for the reaction quotient at the initial conditions for part C. So main thing here is to notice that you are finding the reaction quotient Q by using the exact same expression that you wrote for the Kp expression. The only real difference is that we are using initial partial pressures, so we know that the system is not necessarily at equilibrium. So we're going to use this Q value to determine what's going on in the overall system. The next question is asking us to predict the direction in which the reaction will proceed at 700 kelvins. So the reason it says 700 kelvins is because that is the given temperature for the reaction that we found or have a pressure constant for. So because we have a Kp value and we have found a Q value of 0.165, we just need to compare those two values together. So it may help to unscientific notation our Kp value. So because that's 3.1 times 10 to the minus 4, that's going to be 0.00031 for our Kp as compared to our Q. So again, remember what I said here is that we want to input or compare our values in alphabetical order. So in terms of letter D to our prediction, we're going to be comparing our K value to our Q value. So 0.00031 is much less than the Q value of 0.165. Okay, so because the greater than less than arrow is pointing to the left, that means that the reaction is proceeding to the left. In this case, those initial conditions are going to cause the system to favor the reactants. Okay, in part E, we're also going to go ahead and determine the equilibrium constant for the concentration. So I'm going to go ahead and rearrange the formula for Kc. So I've got Kp over RT to the delta N. Okay, so in this case, I'm going to be plugging in the same Kp that I had before, so the 3.1 times 10 to the minus 4 over my R value 0.0821. Remember, I've got to convert my temperature to kelvins, but in this case, it was already given to me in kelvins. So I have 700 kelvins. And then we're going to raise all of that to the change in moles. So keep in mind that's going to be the number of moles of product minus the number of moles of reactant. So in my ammonia reaction, the one that's towards the top, because that's the one we're talking about, I have 2 moles of product as compared to 4 moles of reactants. So my delta N is -2. Okay, so and make sure again that you apply that delta N to the quantity of R and T, or the product between R and T. So when I do that, I get a Kc of 1.02. Okay, and it kind of makes sense that that's going to be close to 1 if it is an equilibrium system. All right, finally, letter F is asking for some manipulations of Kp values that are, or Kc values that we have. Okay, so we actually have like a couple different parts. Hang on one second so I can scroll down. Okay, so part F, it's already giving me the Kp value. So that value is 8.3 times 10 to the minus 3. All right, so what we're going to be doing is comparing the reaction that is shown. So I'm going to call this letter I and Roman numeral 2, so that we can talk about how you can manipulate your K values easily in order to find your K values for these new situations. Okay, so this information is also in the Bluffer's Guide, and this is something that we'll talk about more once we get to talking about concentration changes. But just for right now, try to see if you can follow along with me. It's going to seem very similar to other things we've done. So, for example, if we're looking at F letter I, or Roman numeral 1, notice that that is the reverse reaction that we were given in the question itself. So in that particular case, since it's reversed, then our Kp value is going to be basically 1 over the value that we had. So 1 over Kp. So 1 over 8.3 times 10 to the minus third is 120. So that's going to be the Kp for the reaction literally written in the other direction. Okay? And if we look at the second equation, notice that it's in the approximately same order. There's a little bit going on differently with the N2 and the 3H2, but if you think about it, that is the same as 2NH3 if with the things broken apart, but it's the same quantity as if we doubled the ammonia. So basically what we did there is we doubled the reaction. And so again, since we're talking about rates, what we're going to do then is square my Kp. Okay, and like I said, the kind of way you can remember that is that we really are focusing more on forward and reverse rates. So when I square that Kp value, I get something like this. So it's going to actually be smaller. It's going to be times 10 to the minus 5. Okay. So just to review, the main goal for this problem in this video was to help you see how Q and K can go together to help tell us more about the equilibrium system, as well as how you can do some basic mathematical manipulations to your equilibrium constant value if you have an overall change in the reaction, such as an inverse or a multiplied case of the reactants. All right. Thank you so much for your time. I hope that was helpful.